Okay, so now in this video here, we're going to talk about bandpass filter circuits. Now there's lots of circuits you can do to get bandpass filters. And the passive one, one of the ones that you can do here is you can actually simply just do Cascade, a low pass filter with a high pass filter. What do I mean by that? Well, let's think about it. So I need a low pass filter. So this is a low pass filter. R1, C1. And let me think about this. Low pass. And the high pass. Yeah, actually I'm going to call this R2 and C2. You'll see why in a second. And then I need a high pass filter cascaded with it. I'm going to call this C1 and R1. Now, and then my output would be right here, V out. Now I'm not going to look at the transfer function for this, but we could look at and solve and find the transfer function for it, but we're going to avoid that for now. But this is a low pass and then a high pass, so we should be able to create a band pass. But we have to think about this for a second. I want to create a high pass filter, so if I were to look at what the Bode plots for these are, we know that a low pass filter looks like this. And we know that a high pass filter looks like this. So we know that's what it looks like. But then we're combining these two together. So we have to be careful because we have these cutoff frequencies, or these corner frequencies, omega, and then another one here of omega. But we have to think about, when I combine these together, what would the one I would want, how would I want to have it as far as the way I want to do this. And so I'm going to draw a picture showing you how we're going to cascade these together, because essentially we're going to multiply the responses together. And so if I have a low pass filter like this, and this is at 0 dB, and then if I have a high pass filter like this, we can see then, if I combine these results, and I'm going to try and do it in a thicker green line here, we'd have that as a result here. So I'm going to even just highlight it so that it's this combining the low pass and the high pass would get me this. Okay, but then let's think about this here. This, of course, corresponds to omega C1 for my band pass, and this corresponds to my omega C2 for the band pass. Okay, but then this here, if I think about it for a second, that's the cutoff for the high pass filter. And this is the cutoff for low pass filter. So it looks a little weird here in the sense that you're saying, well, wait, the higher frequency is actually the cutoff for the low pass filter. So what we're saying here is, if we look at this circuit here, that's why I labeled it here, is omega C2 is 1 over R2 C2, and omega C1 is 1 over R1 C1. So I'm going to write them down here, and we're going to do an example then. So let's look at an example here. So we're going to design a bandpass filter with omega C1 being 100 rad per second and omega C2 being 10 kilorad per second. Now, we're going to just first use the equations to find R1, C1, but the other thing we have to do here, and I'm going to emphasize it up here, you have to account for loading effects for R1, C1. In essence, R1 needs to be approximately 100 times bigger than R2. Alright, so what I like to do on these, when I'm doing these, is first design omega C2. Because that's the one that I don't have to worry about loading effects. So we're going to design omega C2. So we have R times C is equal to 1 over 10 kilorad per second, which would be equal to 10 millirad per second. No, that's not right. Let me use my calculator here. Trying to do this in my head is not a good idea. Yeah, I want to go back there eventually, but I want this. So 1 divided by and so 0.001, so that would be 1 millirad per second. Okay, so in this case, I'm going to maybe make my resistor in the kilo ohm range because I'm going to be dividing by my resistance to get my thing. So I'm going to just let, these are 2, so I'm going to let R2 equal 1 kilo ohm. But then if I do this here, C2 would simply be 1 millirad per second divided by 1 kilo ohm, which I believe if I do my math correctly should be 1 microfarad. No, it's 0.1 microfarads. .1 microfarads. You might want to check my computations. Here, let me just double check this. 1 divided by 10, 1, 2, 3. And I hate the fact that it's not putting it in engineering, but that is definitely 1, 2, 3. So that's 1 millirad per second divided by 1,000. 1, 2, 3, 4, 5, 6. So yeah, that's 0.1 microfarads. Oh, or 100 nanofarads. You could write it either way. Okay, now we need omega C1 needs to be 100 rads per second. But then R2 is equal to 1 kilo ohm. So R1 should equal 100 kilo ohms. Because to prevent loading effects. And so then we know that C1 would just simply be 100 rad per second divided by 100 kilo ohms, which would be 100 divided by 100,000. That's not right. 100 divided by 1, 2, 3, 1, 2, 3. Oh, I guess that is right here. So this is a 1 millifarad capacitor. Okay, well that's a pretty large capacitor, right? So I would probably want to try and get something a little smaller than that. So what I could do here, even though I've already got my loading effect taken care of, you know, let's go ahead, you know, if we increase R1, we can decrease C1. So I'm going to go ahead and step it up, and let's go ahead and, instead of going all the way to the mega ohm range, let's just go ahead and let R1 be, I'll just pick a standard value of 820 kilo ohms, because I'm just making it higher so I can reduce that capacitor size instead of it being a 1 millifarad. So C1 would then be 100 divided by 820 kilo ohms. So let's do that. And so we get times 10 to the negative 4. So that would be 122 microfarad, which is a little bit more reasonable. We can get a hold of a 122 microfarad capacitor pretty easily. It would be an electrolytic, but we can get a hold of that. So now we have reasonable values, because again, if you think here, R2 is 1 kilo ohm, C2 is 0.1 microfarad, 100 nanofarad, and then what we did is we first made sure that R1 was at least 100 times bigger than R2, but even when we did that, we're like, well, wait, the capacitor we got was still kind of big, so we made R1 even bigger, which is fine, because that's just going to even prevent more loading effects, and then we get a little bit more reasonable value for a capacitor. Now, of course, the final thing we need to do is draw the circuit. Now, the bandpass circuit here, remember, we're always doing our low pass first, so this is my low pass stage. And then I have my high pass stage. And you need to make sure to label these correctly. And so this would be 1 kilo ohm, and this was 100 nanofarads. This is 122 microfarads, and this is 820 kilo ohms. And so this would be a bandpass filter using the low and high pass filters that we previously discussed. Now you can see some of the issues here is we do get kind of large value components, which can be somewhat harder to deal with, and especially if you get into higher frequencies, these are not necessarily going to be the best way to do things, but this is a valid way to make a bandpass filter. And in fact, we're going to be designing, in a later lesson, we're going to be designing a simple equalizer for an audio signal that will also do amplification and just kind of go from there. And it'll be a neat little circuit. We'll show it to you later on when we get to it. Alright, so I think that's good enough for this video here. Next video we're going to look at is we're going to look at a different way of doing a bandpass filter. Now again here, let me just emphasize one more thing, maybe. If not given omega C1 or omega C2, find them. Because remember, if we were, for instance, if we were told that the quality factor had to be, let's just say Q1, and that my bandwidth was B1, we can still find omega C1 and omega C2. We can still find those from those equations, and let me just go back here. From these equations, we can find omega C1 and omega C2 from, you know, quality factor. If we're given the bandwidth, you know, and well, the quality factor, we can get the center frequency from the quality factor, you know, so we can get omega C1 and omega C2 then. And then simply once we have omega C1 and omega C2, we would go and use these equations for the design, remembering that you do omega C2 first so that you can ensure that you don't have loading effects by doing that. And actually I should see, it's got to be greater than or equal to it, but the general rule of thumb is 100. Alright, so let's end this video here.